Right, let's put all these ideas together in one curve sketching menu. So we want to draw a good graph now. Things to look for. Points of discontinuity, that's going to create asymptotes, things like that. So bottom of the fraction can't equal 0, or also in this one, because there's a constant on the top of the fraction, we know that fraction can't equal 0, so y can't equal 0. So say that creates asymptotes. In this one, we'd have x equals 0 because of the bottom of the fraction, but also y equals x because the fraction can't equal 0, therefore we can't get x plus 0. Then on our curve, y equals function x, whatever it happens to be, we now know stationary points. That's going to be when the first derivative is equal to 0. So that's the first thing we go looking for. Once we've got them, we want to classify them. So we will use our second derivative. If it's concave down, we know it's a maximum turning point. Concave up, minimum turning point. Then points of inflection. Now the reality is, if they don't ask me to find points of inflection, I'm not going to bother. Because if it's a continuous curve, logically there must be a point of inflection between a maximum and a minimum. So I'm only actually going to go and find it if they ask me to. Or if for some reason I need to know. Maybe I'm unsure what the graph's doing. Point of inflection, the possibility is going to be when it equals 0, but there also has to be a change in concavity. So whether you test either side the second derivative or use the third derivative, up to you. Other things you can tell. We know if the derivative is positive, the curve's going up, it's increasing. If it's negative, it's going down, it's decreasing. If the second derivative is positive, curve's concave up. Negative, curve's concave down. All these things can help us if we're unsure what a picture looks like. So let's do this simple little cubic. We're going to need our first derivative. Our second derivative, for the sake of the example, I am going to find inflection points, so I'll find the third derivative as well. Okay, remember, explain what you're doing. Stationary points occur when the derivative equals 0. I want to find these stationary points. Solve this quadratic. Nicely, 3 goes into everything. So x equals 1 or x equals 3. There's our two possibilities. So let's test those points. Let's see what sort of stationary point they are. When x equals 1, second derivative is negative. So concave down, got to be a maximum turning point. Be careful when you're working out the y value. I see it happen a lot, that people sub it into the wrong thing. You obviously sub it into the equation for y. The number of times I've seen people sub it into dy dx and amazingly come up with a y value of 0, because it's a stationary point, happens a lot. Okay, x equals 3. 6, which is a positive number, so we're concave up, we've got a minimum turning point. As I say, for the sake of the example, let's find that inflection point. It's going to happen when the second derivative is equal to 0, x equals 2. Well, when x equals 2, the third derivative is 6, it's 6 everywhere, but that does not equal 0, so that's telling me that yes, there is a change in concavity. So we know 2, negative 3 is a point of inflection. Let's plot all these points then. There's the maximum 1 minus 1. There's the minimum 3 minus 5. The inflection point 2 minus 3. At this stage it's looking like we've got a straight line. Y-intercept, always easy to find. That's negative 5. X-intercept, I'm only going to find if it's simple to do so. In this case, that cubic's not that simple to solve, so I'm not going to worry about it. How do I get away with it? There's my graph. Notice I stopped it before it got to the x-axis. Okay? So I'm saying, yeah, it goes up there. It'll meet somewhere. I just don't know where. Now, a point, when you're drawing these, don't let the inflection point distract you. It should just happen naturally anyway, because it's changing from concave down to concave up. Just draw a nice smooth curve. It will naturally happen. You don't have to exaggerate the inflection point. Bingo, that's our theory for today. 4F and 4G.